In the last sections, we spent a lot of time talking about how electronic structure was related to chemical properties, and that both were reflected in the group structure of the periodic table. This mode of discussion helps to lay the groundwork for how important electronic structure is for all forms of modern chemistry, but it glosses over the fact that we've been organizing elements by chemical properties since Dmitry Mendeleev started arranging elements by both properties and atomic masses and using the gaps to predict elements. He, by the way, got a Nobel Prize and an element named after him to boot. It's interesting to note that all this work was in the late 1800s, decades before electrons were discovered, and even longer before protons were discovered. So Mendeleev had to use atomic mass, not atomic number. This meant that Mendeleev's work, while correcting many existing errors at the time, had elements misplaced because there are heavier isotopes for some lower atomic number elements. Remember, science is never meant to be linear. When someone corrects earlier research, this is science working, not science failing. One of the skills that we hope you develop as a student here is the ability to understand how to interpret science, both for yourself and for your communities, based on how well something is understood. At the time of this recording, COVID-19 was literally discovered less than a year ago, and frequent corrections are a sign of vibrant research, not the failure of any individual study or body, and it's important to remember that. Our modern periodic table is much more robust now after more than a century of refinement, and there are clearly defined, measurable trends within the periodic table that can put why electronic structure is so important into context, although you will continue to see examples of this throughout all of chemistry. This is a graphic that shows many of the trends we will discuss in the next slides. One of the most straightforward trends in the periodic table is the change that we see in covalent radius. That is, the distance between atom centers when atoms of the same element are bound together. When we move down any column, say from hydrogen to francium, as shown by the red box, the covalent radius increases significantly. This makes sense based on what we know about electronic structure. Each time we move down the periodic table, we've added a shell. That takes space, so naturally it gets bigger. We also notice a general trend as we move from left to right in any row of the periodic table. In general, the left side of the periodic table has a larger radii than the right side. This might not make sense at first glance. We're adding electrons as we move towards the right, but remember that we're also adding protons, which will pull the entire shell closer with the additional positive charge. We talk about this positive charge as Z. It turns out that if you put a bunch of negatively charged electrons between the positively charged nucleus and the outside electrons, the ones on the outside don't feel the positive charge nearly as much. Our trend actually follows then not the nuclear charge, but the nuclear charge that's felt by those outside electrons, the Z effective, the effective nuclear charge. Since adding electrons within a shell does not change the energy of the shell or push out the radiance significantly, Z effective increases relatively consistent across a period, and there's an overall shrinking effect from left to right because there's a higher positive charge felt by that same shell. But as soon as you move to a new shell, there are additional electrons that are held further out. All the electrons we've added in the last period are now core electrons and give a relatively complete shielding, giving a massive decrease in that Z effective and a massive increase in radius. So the general trend here can be explained as larger as you move from helium on the top right to francium in the bottom left in the periodic table. It's hard to see relative size clearly on a big table like we saw before. Here we have the actual covalent atomic radii plotted against atomic number. You can see the largest jumps are when we move to a new shell, helium to lithium, neon to sodium, etc. But within the same group, you can see another trend. All the labeled peaks are the alkali metals from the left of the periodic table, and the labeled naders are the noble gases. While I've waxed on, some of you may have also noticed that while the general trend within a period is decreasing from left to right, there are some noticeable increases. Recall that D and F orbitals are behind in their filling. The D orbitals fill after the next shell has started to be filled, and the F orbitals fill 2 shells behind. So while we're filling the D or F orbitals, we're filling core electrons. Core electrons don't change the outermost shell, yet we're still increasing the number of protons, and therefore the Z effective, the effective nuclear charge. So the radius continues to decrease throughout the entire D block. We see an increase at the end of the D block because at the end of the D block, we're starting to fill the s and p orbitals again. They're starting to fill valence electrons. At the end of the d block, it's actually more stable for atoms to complete the d orbitals at the cost of the s valence electrons. So the d block is actually complete at the low point, even though there are a few more transition metals before the end. And then we see slight increases as we start to add s and p valence electrons. After we add a few valence electrons, the added protons in the nucleus are pulling that outermost shell with greater force again. We have a greater Z effective, and we continue the overall decreasing trend. So the up point is where we move from the D electrons back up to the S and P electrons. The radii of ions, as opposed to atoms, aren't as neatly summarized by periodic trends, since elements across the periodic table tend to form ions with different charges. It's more useful to think about what changes from the covalent radii when an element forms an ion. Looking at the data shown, try to predict a rule based on what you see. We can see that when aluminum loses electrons, it becomes aluminum plus 3. If we think about that in terms of nuclear charge, we haven't changed the aluminum nucleus at all. It still has the same amount of positive, but we've removed all of the outermost electrons. So those left are now the outermost, feeling an increased nuclear charge. So we have a much smaller aluminum ionic radius. Conversely, sulfur gains electrons. Since we haven't changed the nucleus, we haven't added any positive charge, but we've added more electrons, everything is shielded more, and the Z effective will go down. Since there is less overall pull, sulfur's radius increases drastically. So our general rule for ions is that cations quickly become much smaller, while anions become much larger. When we make ions, these ions tend to all want to be in noble gas configurations. Since nonmetals in ionic compounds are anions, they become isoelectronic with the next noble gas. Since metals in ionic compounds are cations, they tend to become isoelectronic with the preceding noble gas. See if you can identify what ions would form from elements 6 to 13, and what their electron configuration is, and which noble gas they are isoelectronic with. You can see that each element from carbon to fluorine will gain just enough electrons to be isoelectronic with neon, all ending up with a configuration of 2s2, 2p6. From sodium to aluminum, each element loses just enough electrons to be isoelectronic with neon, and also ends up with the same electronic configuration, 2s2, 2p6. So all ions of elements from carbon to aluminum are isoelectronic with neon and also with each other. Another easily measurable property of an element is ionization energy, defined as the amount of energy it takes to remove a single electron. Look first at the peaks of each one: helium, neon, argon, krypton, etc. Each of these are noble gases and have complete shells, either a full 1s orbital or a full p orbital completing a shell. Any ionization is very high in energy since it has to destroy a very stable complete shell structure. On the other half of the graph, on the bottom, you have all the lowest values, the alkali metals. Taking any electron is relatively easy, and it gets easier the farther it is from the nucleus because those electrons are held less tightly. So cesium is much easier to ionize than lithium. We also see that even when an S subshell is part of a larger shell, it is still harder to ionize the complete S subshell than the next electron from P subshell. So if you look at the transition from beryllium to boron or from magnesium to aluminum, you see a decrease. Harder to ionize complete S, easier to ionize from the P. You can also see that having an entire subshell half full is also relatively stable. Notice that the nitrogen, 2p3, is harder to ionize than oxygen, 2p4, since ionizing oxygen gives a half-full p orbital. Moving from a full d orbital to a partially filled p orbital, like from zinc to gallium, also results in a significant decrease in ionization. Even going from a full f orbital back to the d orbitals results in lower ionization energies. So hopefully we can see a general trend of increasing as we move left to right and decreasing as we move top to bottom. Alternatively, we can think of helium as the hardest to ionize in the top right and cesium as the easiest to ionize in the bottom left. Even with this general trend, we see that it's always easier to ionize when the result is a complete or half-complete subshell. In this version of the same data, it's easier to see the decreasing trend as you move down groups of the periodic table. Again, if you look at the end of most sections of the periodic table, the end of each subshell, you see that the energy of ionization goes down as you move to the next section, particularly S to P transitions like beryllium to boron and magnesium to aluminum, and D to P transitions like zinc Zn to gallium Ga, or cadmium to indium right below that, or mercury to thallium. Many elements can be ionized multiple times. Again, in this context, ionization is the removal of a single electron, even though we'll often talk about losing an optimal amount of electrons all at once also as ionization. So here, each ionization is moving one electron. The table shown has some of the elements of the fourth row of the periodic table, listed with electron configurations on the left. The lowest ionization you'll see is potassium at the top left, at just over 400 kilojoules per mole. Notice that when potassium is ionized once, it loses only its valence electron and gains a noble gas configuration, which is inherently stable. A second ionization drastically increases the amount of energy required because now the noble gas configuration needs to be broken. So potassium will ionize relatively easily, but just once. Similarly, calcium can ionize once, but even though it's harder to tear a second electron away now that the effective nuclear charge is a little bit higher, the increase is moderate as calcium will gain a noble gas electron configuration. But the third ionization on calcium drastically increases the energy required, again as it's stripping away core electrons from a noble gas configuration. Try to identify the largest jumps in ionization energy for scandium, gallium, germanium, and arsenic, the remaining elements, by looking at the table. For scandium, the largest jump is between the third and fourth ionization energies. This is because both s electrons and the d electrons can be lost, yielding a noble gas configuration after the third ionization. Gallium is at the other end of the d block. Once the d orbitals are all half full, ionizations that remove those 5 d electrons become more rare and difficult, and instead most atoms will only lose s electrons and or any d electrons in excess of 5. Once the d orbitals are completely full, as is the case with gallium, the d electrons will largely stay put, and we can instead remove the 2 s electrons and the single p electron. So its big increase is still from the third to fourth ionization. Germanium has 1 more p electron, so its largest jump is from the fourth to the fifth ionization, and arsenic has its largest jump between the fifth and sixth when it has already lost all of its s and p electrons. This table should give you another way of thinking about how atoms will seek to adopt electronic configurations with complete shells as much as possible. It's a lot easier to ionize until you are at a noble gas configuration, at which point it's much, much harder. The opposite of ionization energy, the amount of energy required to take electrons away from an atom, is electron affinity, the amount of energy it costs to add an electron to an atom. Notice that many of the electron affinities listed are negative, which means that energy is actually released upon accepting an electron. Notice that even the alkali metals at the far left, group 1, which would readily give up an electron, gain energy as they complete their s subshells. They have negative electron affinities. On the other hand, in the second group, going from a complete s subshell and adding an electron to make an incomplete p costs far more energy than many other transitions. Notice also that there's a general trend where the electron affinities are more positive on the left and more negative toward the right, excluding the noble gases. That makes sense because a larger positive effective nuclear charge should allow an atom to accept an electron more easily. So those occur generally further on the right of the periodic table. There's a significant variation in groups, but within the halogens, the carbon group, and the alkali and alkaline earth metals, the magnitude of the electron affinity decreases down the column. Less energy is gained or lost when electrons are added farther from the nucleus. All the trends presented so far are experimentally derived and help to fill out our understanding of electronic structure. Practically speaking, these trends have little direct use. Again, their value is how they support our understanding of electronic structure. Your text deals with the most practical periodic trend, electronegativity, in the next chapter because it's a calculated value rather than an experimentally derived value. However, it is derived from experimental data, bond dissociation energies, and it's much more linear than many of the other trends. Electronegativity essentially defines a relative scale on how much any atom will pull electrons toward itself in a bond, and it's incredibly useful. Excluding the noble gases, the top right of the periodic table is the most electronegative, so fluorine is the most electronegative, and the bottom left is the least electronegative. So within any group, you can generally define electronegativities. The atoms near to the top of a group are going to be more electronegative, and so would carry more negative charge in a bond. Within any period, you can also compare atoms. Atoms toward the right will have a more negative charge, and atoms towards the left will have a more positive charge. This plays a big role in many different ways because differences in electronegativities define different kinds of bonds, polarity of bonds in molecules, and can even explain a lot of the reactivity that we see in organic chemistry. For this reason, being able to judge relative electronegativity without a table is the only trend that is important enough to make it as an essential outcome. Again, you can always judge based on relative position in a row or column. The only outlier is hydrogen, so I usually just remember that hydrogen has an electronegativity between boron and carbon. Many of the trends we talked about are summarized in this graphic. Electronegativity, first ionization energy, and the magnitude of electron affinity increase toward the top right, atomic radius towards the bottom left. You should know the direction of these trends and why, and understand why the electronic structure of an atom leads to small variations in those larger trends. We've talked about ions a little already, but now that we've talked more about the electronic structure of an atom, let's circle back. We know that we can either gain or lose electrons to form an ion. Gaining electrons makes an atom negative, we say anions. Losing electrons makes them positive, we say cations. But now we also know that there are definitely ions that are more stable, those that have noble gas configurations. So when we look closely at beryllium, we know that it will become beryllium plus 2, and in doing so moves from an incomplete second shell to a complete first shell, being isoelectronic with helium. We didn't show chlorine because chlorine is a halogen, but it only needs one electron to become isoelectronic with the next noble gas up, argon. Positions on the periodic table allow us to see that we can make general assertions about the charge of ions in certain parts of the periodic table, particularly the S and P blocks. All of the alkali metals become ions with a +1 charge because they can lose one electron and gain a noble gas configuration. All the alkaline earth metals become ions with a +2 charge. Aluminum can lose 3 electrons for a +3 charge, and carbon, because now it's a nonmetal, is 4 electrons away from being a noble gas, and it can gain 4 electrons to have a -4 charge. The nitrogen group, the pnictogens, gain 3 electrons for a -3 charge. The oxygen group, the chalcogens, have a -2 charge from gaining 2 electrons, and the halogens have a -1 charge from gaining 1 electron. These are easy to figure out from a periodic table because all you need to do is count the positions left to the most recent noble gas to give the charge of a cation, or count the positions to the right to the next noble gas to give the negative charge of an anion. You should absolutely know how to do this, as these atoms are exclusively listed without any indication of charge. The remaining ions that are shown on this table are a list that are traditionally memorized, largely because some of these metals are also traditionally listed without any indication of their oxidation state. However, many of the transition metals that are listed here have more possible oxidation states than the standard list has been updated to include, and it has become increasingly common to indicate oxidation states for many of these ions as well. The exceptions are zinc and cadmium, which both can lose their s electrons while keeping all their d electrons and give a complete shell that's particularly stable, and also silver, that's Ag, which loses a single electron but still maintains a complete fourth shell with d electrons. You should know that zinc, cadmium, and silver have particular cation charges. You'll pick up all the rest later based on use if you actually need them. Some ions are made up from groups of atoms rather than individual atoms. These need to become part of your vocabulary, names and formulas, so that you can quickly recall them as necessary. There are a lot of formulas, but recognizing trends can be a helpful way of making the memorization easier and allow you to retain it better. I'm displaying groups of these ions according to patterns and hope that it makes the memorization easier for you. However, you may find it convenient to refer to Table 3.4 in your text if you'd like to make flashcards so you have them all in one place without any duplicates. In each of these slides, I have also included the acid associated with sets of polyions so you can see the trends associated with the acid names as well. A subset of these acid names I will ask you to memorize in the next chapter. Many of our polyatomic ions have charges less than -1. These polyatomic ions can have hydrogens added as H+ to make related polyatomic ions with lower charge, and the name changes systematically. For example, sulfate is SO4 - 2, which is related to bisulfate HSO4-. Typically adding one hydrogen gives an ion with the prefix bi, but sometimes people also refer to the same ion with hydrogen as a prefix, so bisulfate and hydrogen sulfate are the same thing. Once you add two hydrogens to sulfate, it's now no longer charged and is the fully acidic form. These sulfate ions are notoriously soluble and are therefore really useful in chemistry, and sulfuric acid is a strong acid that's often used catalytically in chemistry. Note that the ate ending for the ion is associated with the ic ending for the acid. We'll talk more about this later as well. We can see the same trend with the phosphate ion, PO4 - 3. Adding one hydrogen gives biphosphate or hydrogen phosphate, HPO4 - 2. Since this still has a -2 charge, adding one more hydrogen still gives a negative charge, H2PO4-. There's no special prefix for two hydrogens, we would just say dihydrogen phosphate, as the di is Greek for two. Like sulfate, phosphate is related to neutral acid, and because phosphate ends in ate, phosphoric acid ends in ic acid. Phosphates occur naturally in your body and can help to adjust pH over a wide range, and are regularly used by biologists to make pH-buffered solutions. This isn't always true, but for sulfate and phosphate, the oxyanions, polyatomic ions that contain oxygen, have the same charge as the simple anion of sulfur and phosphorus, respectively, which makes it easier to remember. So sulfates have a -2 charge, and phosphates have a -3 charge, just like sulfide has a -2 charge, and phosphide has a -3 charge. It should be no surprise that carbonate, CO3 - 2, follows the same pattern of nomenclature. It has a one hydrogen form called bicarbonate or hydrogen carbonate, and a two hydrogen neutral acid called carbonic acid. Again, the ate in the anion is related to ic in the acid name. The carbonate system is enormously important. Not only is it part of your blood pH control, it's also the form that carbon dioxide takes when it's dissolved in water and represents an enormous portion of global carbon dioxide and has a huge influence on ocean acidification. Many ions that we learn are the same central atom with different numbers of oxygen attached. We say that these are at different oxidation states, with the versions with the most oxygens being most oxidized. The version with the most oxygens always ends in ate, while an ite ending refers to one fewer oxygens. For example, nitrate, NO3-, is the most oxidized form of nitrogen, but nitrite, NO2-, has one fewer oxygens. Note that while the ate ending continues to be associated with ic acid in the acid form, ite is associated with the us ending for acids. It's also worth noting that the charge of the ions don't change even while the oxidation state does. So similarly, sulfate, SO4 - 2, is the most oxidized form of sulfur, but there exists also a sulfite ion with one fewer oxygens and the same charge, and its acid form also ends in us. There are actually 4 stable oxyanions of chlorine, which means that we need more than just 2 endings. To indicate something more oxidized than ate, we give the prefix per to an ion, meaning utterly above, as in perchlorate, which is more oxidized than chlorate. Notice that we can still use the ic ending for both acids, as the per prefix distinguishes those. perchlorate and perchloric acid and chloric acid being different. Again, chlorite has one fewer oxygens than chlorate, but when we need to have even fewer oxygens, we're going to call that ion hypochlorite, which, by the way, is the active ingredient in bleach. The prefix hypo means below. You might recognize the prefix from hypothermia, your body being below its normal temperature, being too cold, or hypoxia, your blood oxygen being too low, or any number of similar words. The next ion is permanganate. It's another important ion, manganese in its most oxidized state. Even though we're only learning permanganate, a widely used and beautifully purple oxidant, the name should suggest to it that there also exists a manganate and maybe even a manganite. That's true, but manganate doesn't follow the same rules and is less important, and manganite is not stable. Similarly, carbonate represents the most oxidized form of carbon, CO3 - 2. Its name suggests that there might also be a carbonite with formula CO2 - 2, which many of us, especially Han Solo, knew to be true. Carbonate salts are stable at temperatures of around 15 Kelvin, or less than negative 250 degrees Celsius, which is why I suppose that Han had to be in a carbonite freeze. A few of our ions in an ide, for example, azide and -3. Ide is a general ending to indicate anions that are generally not an oxyanion. They don't have oxygen, including monatomic ions like chloride, oxide, and a host of others that we'll discuss next chapter. I include oxide here specifically because it is related to two polyatomic ions that you should know by the same rules we have talked about. Hydroxide, short for hydrogen oxide, is just the oxide ion with a single hydrogen added. Peroxide can be thought of as a more oxidized version of oxide, where there is now an additional oxygen attached but the same charge. All of these have an ide ending. There aren't many simple cation polyatomic ions, but they all share the same generic cation ending ium. Hopefully this ending sounds familiar. Since most metals tend to form cations in ionic compounds, many metals share that generic ending ium or If you think closely about the metals of the periodic table, it's mainly the metals that have been known for a long time, like gold or silver, and often have a symbol that doesn't match with that name, that don't end in Almost everything that's a metal that's been recently found ends in or eum. In other language, many of these metals actually do follow that form. Gold is arum in Latin, and copper is cuprum, silver is argentinium, and so on. Acetate is a relatively simple form of an entire class of organic anions known as carboxylates, which are the anion form of carboxylic acids. Acetic acid is the carboxylic acid form of acetate, and it's the acid found in vinegar. Derivatives of acetic acid and acetate are common biologically, most notably acetyl-CoA, one of the most central molecules in our metabolism. We have naming systems specific to organic molecules for other chains of carbons and other oxidations, but because acetate is a fairly common ion, we'll get a jump start on organic chemistry right now. Notice that the ate ending is associated with ic acid once again. Chromate and dichromate are both forms of hexavalent chromium, chromium with a 6+ charge. These ions are closely related. They exist in equilibrium. That is, they convert back and forth at most pHs. At very low pHs, which are acidic, both chromate and dichromate are converted to chromic acid, hence the single acid name. At higher concentrations, or pH, dichromate tends to dominate, while chromate, shown by the height of the diagram, is the most represented ion at lower concentrations and mid-range pHs. You can see from the ball and stick models that dichromate is really just two chromates linked by a shared oxygen. So it makes sense that this would happen when chromate is more concentrated. Both of these ions are important industrially. They remain in use along with chromic acid and other chromium-based oxidants as the primary chemical oxidant. In industry, chromate is also used to control corrosion in metals because it can migrate to a material surface and protect that surface from water corrosion. Its use has been declining since 1996 when Aaron Brockovich successfully brought and settled a lawsuit against Pacific Gas and Electric, who had released hexavalent chromium, which is the same as chromate or dichromate or chromic acid, into water in online ponds that contaminated groundwater, which was then linked to a cancer cluster in Hinckley, California. A version of this story is memorialized in the 2000 film starring Julia Roberts. Whether ions come from a single atom or a group of atoms, ions always form in sets. Atoms will gain electrons because others have lost them. The sets are not always right next to each other and are almost never isolated as a set, but we will talk about sets of ions as ionic compounds. If only two elements make up a compound, it's a binary compound. If only a nonmetal and a metal interact, generally they have a large enough difference in electronegativity that they are ionic, so we call that compound a binary ionic compound. Because the electrons gained or lost are always balanced, all ionic compounds are listed in such a way that the total charge will be 0. For our example that we've used before, beryllium chloride, the beryllium is +2. We know that because it's in the second group of the periodic table, the alkaline earth metals, and all of them always have a +2 charge. Similarly, we know that chloride is -1 because it's a halogen. All halogens have a -1 charge. We know that the number of berylliums times the charge will equal the opposite of the number of chlorines times the charge, because the charges have to balance. So if we assume that there's just one beryllium, the charge from that beryllium will be +2. That means the negative charge total must be -2 so that the sum will be 0. And since each chlorine can only be -1, we can divide -2 by -1 to find that we have 2 chlorines. When we actually go to write out the formula for an ionic compound, the cation is always listed first. Again, this is always a metal if it's not a polyatomic ion, and polyatomic cations are relatively uncommon. Hydronium and ammonium are what we've learned so far. The anion is always listed second. Subscripts will indicate the ratio of each, but a subscript of 1 is implied rather than written, as is the case in beryllium, but the subscript of 2 needs to be written because you would have no way of knowing that it's 2 if it's not written. Because anions and polyatomic ions have very consistent charges, the charge of any metal is always known. The charges are never shown in a formula. Notice that we could get the right subscripts for beryllium chloride just by swapping the ion charges. Beryllium's +2 charge becomes chlorine's subscript of 2, and chlorine's -1 charge becomes beryllium's subscript of 1. That would give us the right ratio. In fact, it always gives us the right ratio of things. But since we always are going to use the lowest ratio for a formula, you'll occasionally need to divide by a common factor. Usually that factor is 2. An example would be like magnesium oxide, which has magnesium +2 and oxygen or oxide -2. But it has a formula not of Mg2O2, instead it has a formula of MgO, since both charges could be divided by 2. You'll talk about this more later with Dr. Vanderwood, but I want to plant the seed now because it's related to what we're doing and gives us a useful context for some solubility rules. Not everything that's ionic is equally ionic. Periodic trends really matter for this. The greater the charge density, the more ionic a compound can be. There are two parts to that statement, the charge part and the density part. More charged ions are more ionic. So an ionic compound with a +3 and a -3 charged ion would be more ionic than a compound with only a +1 and a -1 set of ions. The density part relates inversely to ionic radius. Remember, the ionic radius increases as we go down the periodic table, which means that atoms higher in the periodic table, since their electrons can be held more closely, so the ones towards the top of the periodic table are going to be more ionic than the ones towards the bottom of the periodic table. This can be seen clearly in the melting points of ionic salts, although we'll see many more applications. Sodium chloride, for example, only has singly charged ions, +1 sodium, -1 chloride, while magnesium oxide, MgO, has doubly charged ions, +2 magnesium and -2 oxide. Even though the ion sizes are not drastically different, magnesium oxide has a much larger melting point because it is more charged, which makes it more ionic. Ionic compounds may be fairly simple, like sodium chloride, shown in the top left, but they can also have very complex formulas, even including multiple cations, anions, and polyatomic ions. These are particularly common in minerals. Note the presence of some polyatomic ions that you've learned, like carbonate, CO3, hydroxide, OH, and phosphate, PO4. MoO4 is molybdate, a polyatomic anion that you didn't learn. Aside from showing some cool minerals, this is a good chance to remind you once again that the formula is not intended to indicate discrete groupings of atoms in ionic compounds, but rather the formula is just the simple ratio of things that occur in a semi-infinite lattice when they're in the solid state. We have each sodium is connected to many chlorines, each chloride is connected to many sodiums. In minerals, sometimes this is more clear because you can see the sharp angles caused by these repeating crystal patterns, by having all of the individual ions line up in the same way over and over and over again. Not everything that has a formula is an ionic compound. Molecular compounds that consist of discrete units and compounds that have both ionic and molecular components make up for a much larger portion of known compounds than ionic compounds do. Molecular compounds don't fully transfer electrons from one particle to another, making their bonds stronger but much less polar. While they interact very strongly within the molecule, they tend to interact weakly between molecules and so tend to have very different properties. We'll talk in more detail about ionic and molecular bonds in the next chapter.